Good day. In this discussion video, we are going to answer some exercises on arc length parametrization, and curvature of space curves. Here I will present two sets of exercises, and let's start with the first one. For the first exercise, we are given a curve C1 defined by the vector function r with components 2t, 3 sine 2t, and 3 cosine 2t. For 1, we are asked to compute the length of the arc on C1 from t equals 0 to t equals 2 pi. Before we compute for the arc length, let us recall first the formula for L. The arc length L is just equal to this integral. And take note that the integrand, which is just the square root of the sum of the squares of r prime, is just equal to its norm. Hence, to solve for the arc length, we need to find the norm of r prime and take the integral of that from a to b. We get first r prime by differentiating every component of r. The derivative of 2t is 2. The derivative of 3 sine 2t is 3 cosine 2t times 2, which is 6 cosine 2t. And similarly, the derivative of the third component is negative 6 sine 2t. Hence, L, using the formula, is equal to the integral from 0 to 2 pi. This is because we are getting the arc length from t equals 0 to t equals 2 pi of the square root of the sum of the squares of these three components. We have 2 square plus the square of 6 cosine 2t plus the square of negative 6 sine 2t. And we evaluate all the squares. It should result to this one. Now, look at these two components. Here, I can factor out a common factor of 36. So, this will become 36 times the quantity cosine squared 2t plus sine squared 2t. But cosine squared 2t plus sine squared 2t is just equal to 1 by Pythagorean identity. Hence, this 2 sums up to 36. So, you have the integrand as square root of 4 plus 36, which is square root of 40. And since this is a constant, its integral is just simply square root of 40 times the variable t, evaluated at t equals 0 to t equals 2 pi. When t equals 2 pi, you have 2 pi square root of 40 minus when t equals 0, this is just 0. So therefore, the definite integral is 2 pi square root of 40. And simplifying the radical, you have 4 pi square root of 10. Therefore, we can conclude that the arc length of the arc on C1 from t equals 0 to t equals 2 pi is 4 pi square root of 10 units. For 2, we need to prove that C1 has constant curvature, and we do that by getting the exact value of the curvature of C1 at any point. But first, we recall that the curvature of a space curve is the norm of the rate of change of the unit tangent vector with respect to the arc length. And in terms of the parameter t, we have this formula. The curvature is just equal to the norm of the derivative of the unit tangent vector divided by the norm of the derivative of r. And just to recall again, the unit tangent vector is just r prime divided by its norm. From 1, we have r prime of t equals to this one, and also its norm equals square root of 40, which is also 2 square root of 10. So what we do here is we get first the tangential vector t and get the derivative of that, t prime, and get the norm of t prime. Thus, we have the tangential vector to be equal to r prime divided by 2 square root of 10. And we just simply divide each component by 2 square root of 10. And it will result to this one. Now, next we have to get t prime. So just differentiate every component of t. We have that for the first component, this is a constant, so it's 0. Derivative is 0. Here, the derivative is just 3 over square root of 10 times negative 2 sine 2t, or negative 6 sine 2t. And similarly, the third component has derivative negative 6 cosine 2t over square root of 10. So now that we have t prime, we can solve for the curvature, which is just equal to the norm of the t prime we have earlier divided by the norm of r prime, which is square root of 40. So to get the norm, just simply take the square root of the sum of the square of the components. So you have this. By the same argument we had on number 1, I can factor out 36 over 10 here, and these two terms should equal 36 over 10. Hence, this is equal to square root of 18 over 5, which is the lowest term of 36 over 10, divided by square root of 40. Dividing this, you have square root of 18 over 200, or square root of 9 over 100, which is 3 over 10. So this means that for any point, the curvature on C1 is actually 3 over 10, and therefore, and 3 over 10 is a constant, therefore the curvature of C1 is constant. And again, for any point, this should be equal to 3 over 10. Now we can solve this problem in another way. We can solve this using r prime and r double prime. We will use the alternative formula, which is equal to the norm of the cross product of r prime and r double prime divided by the cube of the norm of r prime. So we'll just go through this solution quickly. So setting this up, you have this r prime. To get this r double prime, you have to just get the derivative of r prime. So you have 0 for the first component, negative 12 sine 2t for the second component, and negative 12 cosine 2t for the last component, divided by the norm of r prime of t cubed. And taking the cross product of this, verify that this should equal to this vector divided by 2 square root of 10 cubed. And if you take the norm of this, that you should get 24 square root of 10, and the cube of this is 80 square root of 10. Simplifying this, you get 3 over 10. So we have the same answer as what we had on our first solution. Most of the time, this formula will give us a shorter solution, but you just have to be careful with performing the cross product here. Now let us move on to the second set of exercises. Here we have a curve C2 defined by the vector r with components 4 cosine e to the t, 4 sine e to the t, and 3 e to the t. First, we express the vector r in terms of the arc length parameter s with s greater than or equal to 0 using the point P with coordinates 4 cosine 1, 4 sine 1, and 3 as the reference point. So what we need to do here is to reparameterize r in terms of s, where s here is equal to this integral, and this is just precisely the arc length on the curve C2 from the reference point at t0 to any point at t. So that's why this is called the arc length parametrization. To get the arc length parametrization, we need two things. Based on the formula, we need the norm of r prime and t0. So we solve first for r prime by differentiating every component of r. The derivative of 4 cosine e to the t is just negative 4 sine e to the t times e to the t, which is this one. Similarly, for the second component, we get this derivative, and the derivative of 3e to the t is just itself. Getting the norm of this, take the square root of the sum of the squares, and you should get this one. Now, using the same argument from before, we can factor out 16e to the 2t. So this 2 will just be equal to 16e to the 2t, and then you have plus 9e to the 2t there. This is just equal to the square root of 25e to the 2t, and taking the square root, you have 5e to the 2t. So we have the norm of r prime as 5e to the t. Now, the point P, or a reference point, corresponds to t naught equals 0. So to solve for t naught, you can just equate these three components to its corresponding coordinate here. Let's say, for example, I will choose the third one because it's easy to solve. You have 3e to the t equals the third coordinate 3. So you have 3e to the t equals 3, you have e to the t equals 1, and so t equals 0. So if you check, you can do that for all of the coordinates, and you'll get t equals 0. Okay, or you can also check it by substituting 0 here, and you should get these three coordinates. Thus, setting up the integral for s, you have this integral from 0 to t of 5e to the u du, and so this is just the norm of r prime with the variable replaced by the dummy variable u. So you have the integral as 5e to the u evaluated from 0 to t. At u equals t, you have here 5e to the t. At u equals 0, you have 5e to the 0, or 5. So you have minus 5 here. Now again, our goal here is to replace the parameter t in terms of s. And in our problem, it is enough to replace e to the t because all of the components are in terms of e to the t. Here we have s equals 5e to the t minus 5. To solve for e to the t, we just simply transpose 5 and divide by 5. And we get that e to the t is equal to s plus 5 over 5. So now we have this arc length parametrization with e to the t replaced by s plus 5 over 5. For the second problem, we need to find another point Q on C2 such that the arc length on C2 from P to Q in the direction of increasing parameter is 5 pi minus 5 units. Now this is easier to solve now because we have already the arc length parameter from number 1. So if you are given an arc length from a point P to Q, and you have the arc length parameterization from the reference point P, to find the coordinates Q, you can just simply substitute the value of the arc length, which is 5 pi minus 5 units, to the arc length parameterization we have from number 1. So this is just a direct substitution to that, and you have this one. Simplifying this 3, you'll get 4 cosine pi, 4 sine pi, and this is just 3 pi. But 4 cosine pi is negative 4, 4 sine pi is 0, and the third coordinate is 3 pi. So therefore, point Q has coordinates negative 4, 0, and 3 pi. Alternatively, if we don't have the arc length parameterization, first, you can do it in another way. Suppose point Q corresponds to t equals b. So we just simply take the arc length on C2 from t equals 0 to t equals b. So you have this integral of 0 to b of the arc length, but of the norm of r prime, but the norm of r prime is just 5e to the t, and the integral is 5e to the t evaluated from 0 to b, which is just 5e to the b minus 5. So now we have that 5e to the b minus 5 is just equal to the arc length in the given, so 5 pi minus 5. You have e to the b equals pi, so we cancel out 5 and divide by 5, and you have b equals ln pi. So therefore, our point Q corresponds to t equals ln pi. So to get the coordinate, you just simply substitute t as ln pi in this component. So you have 4 cosine e to the ln pi, 4 sine e to the ln pi, and 3e to the ln pi. But ln pi, e to the ln pi again is pi, so you just have 4 cosine pi, which is negative 4, 4 sine pi, which is 0, and 3 pi as the third coordinate. So here we have the coordinate equal to what we had using the arc length parametrization. Okay. But again, if you have the arc length parametrization, it will be easier for you to get the other point just by substituting the arc length on the arc length parametrization. Lastly, we need to compute for the curvature of C2 at the point where t equals ln pi. So again, you can do this using two formula, but let me use the alternative formula, which uses r prime and r double prime. From the previous two items, we already have r prime as this. So to get r double prime, just simply take the derivative of the components of r prime. So note here, this is a product of two functions, so you have to use product rule to differentiate. And you should get this derivative. You'll do the same for the second coordinate, use product rule again, and you'll get this derivative. Lastly, the derivative of t to the t is just itself again. Now, we're getting the curvature at a specific point where t equals ln pi. So, we can already substitute ln pi to both r prime and r double prime. So, for first, we have r prime of ln pi. So we note here first that e to the ln pi is just equal to pi. So if I substitute ln pi here, I have negative 4 pi sine pi, which is just 0. Here you have 4 pi cosine pi, which is just negative 4 pi. And you have here 3 pi. Similarly, you substitute ln pi here. So here you have, if you have e to the 2t, you'll get e to the 2 ln pi, or e to the ln pi square, which is just equal to pi square. So this is just equal to pi square. You have negative 4 pi square cosine pi. So cosine pi is just negative 1. So that's 4 pi square. And you have here minus 4 pi sine pi. So this is just 0. So the first coordinate is 4 pi square. Okay. So you just substitute ln pi again to this one. You should get negative 4 pi. And here you have 3 pi. So now that you have r prime and r double prime at t equals ln pi, we can take the curvature. So recall that this is the formula for the curvature. You have the norm of the cross product of r prime and r double prime divided by the cube of the norm of r prime. So just substitute the coordinates the vectors that we had earlier. And if you take this cross product, it should equal to this one divided by, so the norm of this will just be square root of 0 square plus 16 pi square plus 9 pi square, which is just square root of 25 pi square. And taking the norms, the norm of the numerator, you'll get square root of 144 pi to the 6 plus 256 pi to the 6. And for the denominator, you have there 5 pi raised to 3. So that's 125 pi cube. So this now is equal to square root of 400 pi to the 6. Taking the square root, you should get 20 pi cube. Then you have 125 pi cube. So cancel out pi cube, and expressing this in lowest term, you'll get 4 over 25. Hence, we have the curvature of C2 at the point where t equals ln pi is 4 over 25. So you can also use the other formula for this, which uses the norm of the derivative of the unit tangent vector divided by the norm of r prime. And here are more exercises that you can answer on your own. Let me just add here for number 2 that the radius of curvature, which is also the radius of the oscillating circle, is just the reciprocal of the curvature. And that ends our discussion. I hope you were able to understand the exercises well. Goodbye.